In this video, I will look at the details of the hydrologic cycle. Many important terms and concepts are going to be discussed in this video. These are terms and concepts that we will use heavily throughout the remainder of this course. Chief among them will be the equation for hydrologic equilibrium. So keep that in mind. Here we go. Here is the textbook illustration of the hydrologic cycle. We start with the precipitation in the form of rain or snow, which can flow across the landscape as overland flow or runoff. Some of the water engages in evapotranspiration, and that's either direct evaporation of the water from free surfaces or transpiration from plants. Some of the water infiltrates, and it infiltrates through an unsaturated or vadose zone at the top. At some points, there's a perched water table where the hydraulic conductivity is such that water cannot sink all the way through the unsaturated soil and gets hung up in a higher level. And then there's the water table, where below the water table the soil and rock is fully saturated. Along the surface of the water table there is a capillary fringe where surface tension effects pull the water up into the unsaturated zone or partially saturated zone. Finally, there is a saltwater wedge, because saltwater is denser than fresh water and tends to wedge in under the groundwater beneath the continental regions. The water balance in the world is given in this table. As you can see, oceans represent 94% of all water on Earth's surface. Ice caps and glaciers account for another 2%. We're up to 96%. And groundwater then represents 4%. So between oceans, ice caps, and groundwater, we can account for essentially 100% of all water. You see lakes, rivers, swamps, soil, atmosphere, biosphere water is all minuscule in comparison with the big three: oceans, ice, and groundwater. Another interesting set of statistics on this table is the average residence time in the various reservoirs of water. In oceans, water hangs around for up to 4,000 years between when it comes in rivers and streams and when it evaporates to return to the land. Ice caps and glaciers have residence times for water that can be from decades to millennia, and likewise groundwater has a very large range of residence time from weeks to many millennia. So the key concepts: precipitation goes either to overland flow or runoff, or to interflow, and I'll illustrate that in a moment, or to evapotranspiration, which is the direct evaporation and plant exhalation. And finally, it can go to infiltration. The infiltration is what it makes it into the groundwater system. And as a rule of thumb, 10% is a typical amount of infiltration. So, groundwater includes water in the vadose zone or zone of aeration. That's the partially saturated zone between the surface and the water table. Within the vadose zone, capillary effects, the surface tensions of the water interacting with gravity and the surfaces of soil and rock, give rise to its properties. There is then, below the vadose zone, the capillary fringe above the water table. It's a zone of saturation above the water table where water is drawn up by capillary suction. Finally, we have the water table, and beneath the water table, it is the zone of full saturation of the rock. At the surface of the water table, the pore pressure of the water is equal to atmospheric pressure. Above the water table, we can have perched water tables which pond up on zones of low hydraulic conductivity. So we have recharge, which is water entering the groundwater system through infiltration or from the surface water. Discharge, which is groundwater leaving the aquifer system, usually going to the surface or other water systems. And finally, there's water in storage, the water that is within the groundwater system. Now we can state the hydrologic equation, which is just basically a conservation of mass, or we could call it the water budget. Outflow is equal to inflow plus or minus changes in storage. This equation is applicable to surface features like lakes. Stuff comes into the lake, stuff flows out of the lake. If more flows in than out, then water is increased in the lake. This change in storage is positive. If the outflow is greater than the inflow, then the lake loses volumes of water. It's applicable to rivers, it's applicable to aquifers, and it's applicable to whole basins, including multiple aquifers. So let's look at the water budget averaged over the entire United States. The amount of precipitation is about 30 inches of rain. So that's 30 inches distributed over the entire continental surface area. Multiply the surface area times 30 inches and we have a volume of water that rains down to supply everything. Now 22 inches of that 30-inch evaporate or are transpired by plants. So you see that most of the water that rains goes back up in evaporation or evapotranspiration. Finally, 8 inches of that water flows into the ocean from rivers. So where's the groundwater in this? Groundwater is a larger component of water than in any of the rivers or lakes. It's estimated that there's 70 times more groundwater than surface water. So we need to look at the hydrologic equation. We have inflow of 30 inches. We use a rule of thumb saying that about 10% of the water infiltrates. So of the 30 inches of precipitation, 3 inches of it get into the groundwater. Since the groundwater outflow is going to equal the inflow plus or minus changes in storage, we have outflow is equal to 3 inches plus or minus changes in storage. If the amount of groundwater is constant, then the outflow has to be 3 inches. So 3 inches in, 3 inches out. Thus, of the 8 inches of flow to oceans in rivers, 5 inches of that represents that which is direct runoff, and 3 inches of the 8 is discharge from aquifers. Let's focus on some of the details of evapotranspiration. And we will finally determine groundwater recharge from streams. So let's look at evaporation. It's a thermodynamic process. You put in energy and it moves molecules of water from the liquid to the vapor phase. Works out to be 590 calories per gram of water. In equilibrium, air has a maximum amount of water vapor. We call this the saturation humidity. The saturation humidity depends on temperature. With temperature higher, the saturation humidity goes up. So let's go through some terms. Absolute humidity is the mass of water that resides in a volume of air. We can describe that in units of grams per cubic centimeter, or mass per volume. There's relative humidity, which is the ratio of the absolute humidity to the saturation humidity. And since we're dividing grams per cc into grams per cc, the relative humidity is a dimensionless number. Dew point is the temperature at which the air has 100% relative humidity. So the driving terms for evaporation: you must have free water surfaces, then temperature, relative humidity. As you put the temperature up, evaporation increases. As the relative humidity goes down, evaporation increases. We need energy, principally from the sun. We have a flux of about 1 kilowatt per square meter at noon. And we'll use the energy unit of Langley, which is a calorie per square centimeter, which works out to be 41.8 kilojoules per square meter. And working through conversions, that means that a unit of energy of 500 Langley is equivalent to 6 kilowatt hours per square meter. So in northern U.S. during the summer, a typical average summer day would have a total energy of about 500 Langleys. Finally, there's wind. Wind replaces saturated air near the surface with less saturated air, and it also disturbs the water surface to enhance rates of molecular diffusion. So higher the wind, the more the evaporation. So we need to quantify all this. Unfortunately, even with accurate measurements, it's unlikely that we'll know evaporation to better than about 10%. The USGS maintains about 450 land pans, and these are 4-foot by 10-inch unpainted galvanized metal pans on stilts, so it allows airflow on all sides. There's a daily record taken of how much water is added to the pan in order to maintain the level of water. Separate rain gauges are used to measure precipitation. And then one can measure the amount of wind, and it's usually quantified in wind movement as miles per day. A pan coefficient is determined empirically to estimate how much water evaporates from a freestanding body like a lake, which is going to be different than the amount of water that evaporates from this unpainted galvanized pan. All this information has been put together in nomographs, and I'll walk you through a calculation of the daily evaporation using a nomograph. Let's take as an example that the temperature on a given day has a mean value of 76 degrees. The insolation is 500 Langleys. That's how much solar radiation there was during the day. The dew point on average throughout the day was 50 degrees, and the wind movement for the day was 200 miles. So we want to calculate the amount of evaporation from a standing body of water using those 4 bits of information. Now, it is a formula involving 4 inputs and 1 calculation, and it can all be put together into a graph like this, which has in the upper left contours of insolation, on the upper right contours of dew point, on the lower right contours of wind movement, on the lower left values of evaporation. So what do? We go to the scale on the upper left side, which shows temperatures in degrees Fahrenheit, and we draw a line across at the average temperature for the day, 76 degrees in our example. We note on the graph where this straight line intersects the solar radiation curves and the dew point temperature. We draw a vertical line from the solar radiation of 500 Langleys downwards, and we draw another vertical line from the mean dew point of 50 degrees. We take the dew point of 50-degree line and find where it crosses the wind movement diagram at 200 miles per day, and we draw a horizontal line back across. It is the intersection of the final 2 horizontal lines that define the amount of daily evaporation. In our example here, about 1/4 of an inch would evaporate from a standing body of water. Now, transpiration. is a more difficult proposition. Plants pump water into the air. The amount they pump into the air is variable with season. During the growing season, they'll pump more in than when they are dormant. It also depends on the time of day. Plants need sunshine to be chemically active, biologically active. And finally, the amount of water they can pump in the air is limited by how much is available in the soil. If not enough is available, the plant will reach a point at which it wilts. So, transpiration can be measured under lab condition, but it's not an easy proposition to measure it in the field. We combine both evaporation and transpiration together, calling it evapotranspiration, or ET for short. And for the remainder of the course, we'll consider ET as the practical value to include in our calculation. Now, ET has a potential value and an actual value. The potential value is sometimes determined by the Thornthwaite method, and it relies on meteorological conditions. We can also do an energy balance method, calculating solar radiation energy input to the ground, heat loss, heat of vaporization, and so forth. We could also set up a lysimeter. So this is our experimental method. We put a container of soil together, plant it with the vegetation of interest. We measure the inputs and outputs. We measure how much water we have to put into the tub in order to keep the plants alive. These graphs illustrate potential evapotranspiration from the actual evapotranspiration. So the curves denoted with open squares are calculated from a Thornthwaite method, and you can see that the potential evapotranspiration peaks in the summer when insolation and heat is largest and becomes smaller during the winter. Now, the potential evapotranspiration is modified by the fact that you have to have water available in order for it to be transpired or evaporated. In the curve on the left, we have a situation in which rainfall during the summer is low, and thus, during the time when potential evapotranspiration is largest, the available water is least, and the actual evapotranspiration is much less than the potential evapotranspiration. You can see that during the winter months, when there's abundant rainfall and low potential evapotranspiration, actual ET and potential are in agreement. During the summer months, they are in disagreement due to the lack of water. The curves on the right show an example in which rainfall is more evenly distributed through the year, and thus the actual ET during the summer comes closer to the potential. Okay, so let's talk about general trends of ET. ET is, in most climates, the dominant use of water. For instance, we already looked at the continental U.S. budget, and out of 30 inches of rainfall on average, 22 inches of it goes to ET. Runoff typically picks up after land is logged, thus the ground with the removal of the trees supports less evapotranspiration, so the runoff increases. In Arizona showed that a transition from natural chaparral to grazing land generated less evapotranspiration, since the grass could not suck the water as deeply from the subsurface. Sagebrush to grass in Colorado didn't change evapotranspiration, but more grazing decreased ET because there was a smaller amount of biologic material to undertake ET, or transpiration. The transition from farm to forest is usually associated with a decrease in stream flow. So The forest transpires more water and allows less to make it into the stream. Evapotranspiration is greater in coniferous forests, fir forests of the Northwest, than deciduous forests. Evapotranspiration is larger in urban areas. There's less runoff in dry period, and although there's more pavement, patterns of planting tend to encourage evapotranspiration in urban areas. So let's look at the water that doesn't go into evapotranspiration. We start off with the rainfall striking the surface. Much of the water then flows across the surface as overland flow. That's fast. Some of the water sinks in and flows along interfaces between the most highly permeable surface layers and the deeper, less permeable layers. We call that interflow. It has a lower speed making it into the stream than the overland flow, but it's still fairly fast. And finally, some fraction of the water infiltrates the low permeability bedrock and becomes part of the aquifer system. And the green line then shows the flow of water within groundwater to the stream from recharge areas. That's the slowest transport. So now it's time to look at the stream flow, and here is a stream hydrograph. Hydrograph is a measure of discharge of a flowing body of water, plotted usually as a function of time, typically plotted in not calendar years but in water years. Water year begins in most regions of the United States in October. So the plot has a vertical scale of cubic meters or cubic feet of water per second. The horizontal scale is time. You can see during the winter months when precipitation is higher that the stream flow increases. The individual peaks showing up on the hydrograph represent precipitation events. It's times in which the water, the precipitation generates overland flow and interflow, which feeds into the streams quickly and raises the discharge. Now, during times with little precipitation, there's no overland flow, there's no interflow, so the only source of flow for the stream is discharge from the aquifer. This discharge from the aquifer is called the base flow. So you see on here this declining rate of flow as the aquifer is drained during the summer months, and you see at the beginning of October then precipitation begins again and the stream flow increases. So how do you separate in a hydrograph the contributions of overland flow, direct precipitation, interflow, and base flow? Let's illustrate it with starting with the diagram at the top, which shows the total stream flow. And you'll notice that there's a period of precipitation, a precipitation event. Prior to the precipitation event, the stream flow is fairly low. During the precipitation, the stream flow increases as overland flow, direct precipitation into the stream, and interflow contribute to the discharge. After the precipitation turns off, there's a decline, a rapid decline in the discharge as the overland flow and the interflow decline, and finally there's a return to a base flow level, but as you notice in this diagram, the base flow is slightly higher than it was to begin with. So let's separate it out. Here is the overland flow component of that diagram. Here's the base flow. So you see that the base flow is low to begin with, and it ramps up as infiltration increases the amount of water in the aquifer, and it comes up then to a higher level following the precipitation event. The direct precipitation, that's the water that fell directly into the stream. That's usually a fairly minor component. You see it's timed directly in the time that rainfall was occurring. And finally, here's the interflow. It's delayed somewhat from the beginning of precipitation. The water hits the ground, infiltrates in the shallow layer, runs along the shallow interface, and finally into the stream. In many cases, the interflow is a small component compared to the overland flow. So here is a hydrograph representing a single precipitation event, and on that we have indicated the overland flow component and a base flow component sketched in with a dashed line. The base flow component, you see, becomes the dominant component after about 7 days after the beginning of the precipitation. So there is a duration of surface flow illustrated as D from the peak of precipitation out to the point at which base flow dominates again. And there's a rule of thumb supported by empirical data that's given at the top that the number of days is equal to the watershed area raised to the 0.2 power. This is not a fundamental theory, it's not dimensionally correct, but it gives a rule of thumb for what to expect. And for instance, a 1 square mile watershed would have about 1 day of non-base flow, whereas a 10 square mile aquifer would have 1.6, a 100 square mile aquifer would have 2.5 days, and a 1,000 square mile aquifer would have 4 days of overland flow. Now, the textbook has a section on determining stream discharge. It's very interesting. I'd recommend that you read it, but I won't include it on quizzes or tests for this course. The textbook also has a section on measurement of the distribution of precipitation, and I have assigned homework in which you will create isohydal lines and Thiessen polygons. I'm not going to lecture on that material. I'll leave that for you to look at while doing the homework. Finally, I want to talk about the estimation of groundwater recharge from the base flow recession.